The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So remember last time we learned about the cross product of vectors in space. So remember, the definition of cross product is in terms of this determinant I hat, j hat, k hat, and then the components of A, A1, A2, A3, and then the components of B. And this is not an actual determinant because these are not numbers, but it's a symbolic notation to remember what the actual formula is. And the actual formula is obtained by expanding the determinant. So we have actually this smaller determinant, A2, A3, B2, B3 times I hat minus determinant of A1, A3, B1, B3 times j hat plus determinant of A1, A2, B1, B2 times k hat. And we also saw a more geometric definition of a cross product. So we've learned that the length of the cross product is equal to the area of the parallelogram with sides A and B. We've also learned that the direction of the cross product is given by taking the direction that's perpendicular to A and B. So in fact, if I draw A and B in a plane, they determine a plane together, then the cross product should go in the direction that's perpendicular to that plane. Now, there's two different possible directions that are perpendicular to a plane, and to decide which one it is, we use the right-hand rule. Which says if you extend your right hand in the direction of vector A, then curve your fingers in the direction of B, then your thumb will go in the direction of the cross product. Okay? So one thing I didn't quite get to say last time is that there are some funny manipulation rules. What are we allowed to do or not do with cross products? So let me tell you right away the most surprising one, maybe if you've never seen it before. It's that A cross B and B cross A are not the same thing. Okay. Why are they not the same thing? Well, one way to see it is to think geometrically. Sure, the parallelogram still has the same area, and it's still in the same plane, so it's still perpendicular to the same plane. But what happens is if you try to apply the right-hand rule but exchanging the rules of A and B, then you will either injure yourself or you will end up pointing in the opposite direction. Okay? So in fact, B cross A and A cross B are opposite of each other. And you can check that in the formula because, see, for example, the I component is A2B3 minus A3B2. If you swap the roles of A and B, you will also have to change the signs. Okay, so that's a slightly surprising thing, but you'll see one easily adjusts to it. It just means resist the temptation to write, AB equals BA. Whenever you do that, put a minus sign. Now, in particular, well, what happens if I do A cross A? Well, I will get 0. And there's many ways to see that. One is to use the formula. Also, you can say just that, the parallelogram formed by A and A is completely flat, and it has area 0. So that's the 0 vector. Okay. So hopefully you got practice with cross products and computing them in recitation yesterday. Let me just point out one important application of cross product that maybe you haven't seen yet. So let's say that I'm given 3 points in space, and I want to find the equation of a plane that contains them. So say I have P1, P2, P3, 3 points in space. Well, they determine a plane, I mean, at least if they are not aligned. And we would like to find the equation of a plane that they determine. So that means, let's say that we have a point P in space with coordinates x, y, z. Well, the equation of the plane let's say the plane containing P1, P2, and P3. So that means find a condition. We need to find a condition on the coordinates x, y, z telling us whether P is in the plane or not. Okay, so we have several ways of doing that. For example, one thing we could do, let me just backtrack to determinants that we saw last time. So one way to think about it is to consider these vectors P1, P2, P1, P3, and P1, P. Okay? So the question of whether they're all in the same plane is the same as asking ourselves whether the parallelepiped that they form is actually completely flattened. Right? If I try to form a parallelepiped with these 3 sides, well, if P is not in the plane, then it will have some volume. But if P is in the plane, that means that it's actually completely squished. So one possible answer, one way to think of the equation of a plane should be that the determinant of these vectors should be 0. Determinant of P1, P2, P1, P3, and actually let me do it in a different order. It doesn't really matter, but so one possible way to express the condition that P is in the plane is to say that the determinant of these 3 vectors has to be 0. And if I'm given coordinates for these points, I mean, I'm not giving you numbers, but if I gave you numbers, then you would be able to plug these numbers in. So you could compute these 2 vectors explicitly. You would have numbers here. But here, of course, this would depend on x, y, and z. So when you compute the determinant, you get a formula that involves x, y, and z, and you will find that this condition on x, y, z, that's the equation of a plane. Okay, so we're going to see more about that pretty soon.